I saw the program, and actually you have a quite large overview now about the magnetic field from the core, from the external field magnetospheric. So this is about the ionospheric field, and this is a very nice introduction because the magnetic lithospheric field is well below the signal of all these fields. So the purpose now is to extract this signal from a bunch of measurements that are sparse, non-equally distributed, and sometimes require over long time periods. So I will start with a small movie. Yes, this one is reacting very slowly. I think it's time for that. It's starting. So this is the vertical component you will measure from space. It's the core field. Well, this is the total actually. And you see the scale. It's between, let's say, 60,000 Tesla plus minus. And now the purpose is to correct for this field, to highlight the lithospheric field. So now I'm doing the other way around because I'm showing you the final result, which is the final model. And this is something you get after a lot of data processing. Yes, so it's rotating. So this is just for showing you how the scale decreases. Now we are going down to the Earth's surface, and this is about 100 to 1,000 times lower than the core field signal. And obviously, you see a lot of structures that are very difficult to understand, or at least to interpret. And also, this is only a partial view because the core field is masking the large scales of the lithospheric field. Everything is embedded, and we cannot reconcile all information into a significant model for the core field, for the cluster field. So those are just a few explanations. I will not go into details of these ones. Just to show you the scales. Remember the scales, we start from something like 60,000 nanoteslon, going down to a few hundreds. And at satellite altitude, it's even lower. So this field can be extracted after correction for the core field. You had a very nice talk about that, and you will see that this week, next week, that there are full sessions for the core field from the dynamic geodynamical simulations to the observations. You also had some information this morning about the magnetospheric field, and I'm not using all the details of this magnetospheric field, but we use the experiments they have to improve our corrections, and so there is a kind of circular loop between all these people from the external field and us from the internal field. The problem also is that the Earth's crystal field, we call it equivalently sometimes lithospheric field because we don't know exactly where is the boundary. We think that magnetization stops around 550 degrees Celsius, so it should not be in the mantle because of the thermal regime of the Earth. But it's not clear whether this mobile discontinuity that defines the crust is the actual magnetic boundary. So in some places, it may be, for instance, in subduction zones, for instance, if we have something that is very rapid and is going in the mantle, it's not magnetized mantle, but it's magnetization in the mantle. So we put it in the lithosphere just for being more cautious. And the thing is that the field can also be induced and remnant. So in paramagnetic field, we use mostly remnants because it's locking, it has locked the direction of the ambient field over the ages, but it also can be induced, which means that it's dependent on the geometry of the actual field. And both information are superimposing to give you the total crystal field. And the challenge is to separate between both components because even the remnant magnetization can be aligned actually along the actual field by chance. So this is another view because you saw that spherical harmonics, everybody is familiar with spherical harmonics. Who is not familiar with spherical harmonics? Not familiar at all? Okay, so briefly, spherical harmonics are a mathematical method that we use extensively for modeling the global field. They rely on spherical harmonics, that solves the Laplace equation. And so you can extract the wave numbers and information wave number by wave number to build up the spectrum. So it's kind of compaction of measurements. And what you see if you just take all the sources of the magnetic field, that you have this long-term co-field. And here this is the wavelength of spherical harmonic degrees is inversely proportional to wavelength. So this one will be the largest wavelength, which is the size of the Earth. And this one will be 400 kilometers. And you see that the core field is dominating all other sources, but it's varying over quite slowly on a circular time scale, even though we have geometric jerks, you know, that's the average acceleration of the field. But the signal is not very strong. And then on the same branch, you have this ocean circulation induction effects, but you see the strength is very low, so it's not really a problem either. But this stuff here, magnetospheric currents and mid-latitude currents are very problematic because statistically you can extract the features, the one you saw this morning. But on top of that, you have a lot of truncheon fields, and these truncheons are completely unpredictable. They really depend on the geometry of the magnetospheric, the solarium, the number of the species in the upper atmosphere, and how the reflections are carried out. You heard about turbulences. And so it's very difficult to monitor them very exactly unless you measure at the same time the magnetic field everywhere on Earth. So then you can separate between what is spatial from what is only temporal. So if you go, the problem also is that there are some other currents there, but some of them are rapid, and the chance we have is that the lithospheric field is supposed to be quasi-static, so you can accumulate the signal over time. And this, after some time, improves the signal to noise ratio to get you a kind of broader picture. So the thing is that if you take at the radius of the Earth the energy of the total lithospheric field over the core field, it's about 0.5%. So it's small. But if you go at 400 kilometers altitude, which is the altitude of the low Earth or satellites, it's decreasing to 0.01%. So it's a very tiny signal, very weak, and also the problem is the satellites are moving very fast. It's 7 kilometers per second. So it means that you have 1 data every 7 kilometers if you use the standard manipulator. So the spatial resolution is obviously lower because you are just scattering the actual field is determined from very remote discrete points. So this is another picture showing how it was prepared during the preparation of the European formation. So this is the core, showing you again scales. If you remove the core, then you have the magnetospheric field. So now you see the scales are decreasing drastically, but here it's showing only the statistical field, but around the statistical field you have a lot of rapid variations. So this is 3 times above the range of the crystal field at the satellite latitude, and also you have ionospheric field where you have kind of a dynamo happening during daylight, and so those are small scales, and they are also problematic for the crystal field. And then after that you have the crystal field. See the scales, it's 5 to 6 times smaller than the microscopic field. And if you remove the crust, I'm not talking about this today, but one of the most challenging signals to catch is the signal from the ocean, which is very interesting because it's following the tide. Okay?
This is at secondary altitude.
Yeah, here it's just a satellite altitude. It's a simulation of satellite altitude. It has nothing to do with the small scale altitude. Okay, just as a general introduction, you don't really need that, but we can work with different coordinate systems, Cartesian, spherical coordinate systems. So the thing is that the vector field, the first step is the vector, and sometimes you can measure only the intensity. And so we have some ambiguities that we need to resolve, and also you have to you have to account for, because sometimes it is in use, you have to account for the declination and inclination of the total Earth magnetic field, just to correct everything. I will show you examples later. So now, why do we have a crustal field? It's not really clear because the thing is that we don't really care about the crustal field. What we are interested in are the properties of the crust. And the properties of the crust are structures, relations to tectonics, compositions, sometimes heat flow. And the magnetic field is something that we measure because this is the effect of many parameters. And sometimes we measure it, we always measure it outside the sources. So it's very difficult to go back or to extract the information corresponding to the composition of the Earth's crust. But what you can see is that on some places, depending on the rocks, you have an effect of rocks on a simple compass. So here, this is just an example done on the Eastern Island. So it's kind of Niemegk stone. And you see that, you don't see it, but it's pointing towards the stone because the stone acts as a magnet. So it's changing the direction of the magnetic field. So this is how we will recognize the crustal in the lithospheric field. So this is the perturbation of rocks of the ambient field. So it's not exactly crustal or lithospheric field. This is just an anomaly with respect to everything we know. So sometimes we are making mistakes. So the thing is that for this kind of stone, for instance, this is a volcanic island. So you have a mixture of the induced magnetization, and there is no point to separate these two information at the moment, but these things lining up in the crust and over large distances will create kind of signal that is what we call the lithospheric and the prospective signal. So I'm not much into these details because I'm not very comfortable with them. Maybe we can know much more about this, the property of rocks at the smaller scales, because paleomagnetism is about that. How you measure the magnetization of rock and how you replace this magnetization by something you know to extract the susceptibility parameters and also the renal magnetic field. But the thing is that rocks are it's a composite of many different minerals, and they change all the time. They change with time, they change with chemical alteration, they change with erosion, they change with pressure, they change depending on where they were generated, deep in the mantle, deep in the crust, or on top of that. And when you look at the microscope, you see a lot of crystals, and here, for instance, it's an iron. And the challenge now is to make table in the lab, two for each mineral, just to make kind of value for the susceptibility, and try to make kind of extensive table of all minerals on Earth to have an idea about how they will respond to the Earth's core field. So the thing is that you have the macros, very small scale, you have currents, electric currents or spins, and we have seen this picture many times this morning. You just use your hand, and when you have a current spin, you have a magnetic field creating. So at a very small scale, you can have magnetic field in many directions. And then what you measure, even when you have a sample, it's kind of bulk magnetization. So it's already something statistically different. And if you use different samples, you will have another bulk magnetization that probably doesn't give you the same either direction and value. So you play with this. So another thing that these kind of properties can be used in many areas. So we are talking about the crustal field, but you can use it for inferring what is in the near subsurface. So prospecting, geophysical prospecting is all about that. Trying to see the contrast. And you can use it also in archaeology, because if you have potteries, some of them were baked or are baked, and then the heat has destroyed magnetization, and when it cools down, it has lost magnetization, so it's just creating an anomaly in the subsurface. And so you don't really need the direction in this case, just that this is seen as an anomaly when you go with the magnetometer. You see, compared to the surrounding, there is a contrast here that can be highlighted. Doesn't give you any information about the depth, it's just giving you a map. And then you can have archaeologists to dig, and sometimes they find walls, sometimes they find pottery, this kind of stuff. But it's not an Owen, an archaeologist. Yeah. Sorry? Whatever. This one is missing. I mean this number. So just to bridge some gap with paleomagnetism and also archaeomagnetism, this principle is also used to reconstruct the intensity of the field over time. For instance, here you have artifacts, and some of them are used for the pavements of the church, for instance, and so they are recorded in the books. So you have the date, and then you measure in the lab the magnetization, and you just then after it's adding a point at some times where direct measurements were not available. And interestingly, if we ever wanted to extract the crustal information back in time, which is something that is never done, this kind of curve helps you to reconstruct the core field over long time periods, and then if you want to use this core field to correct the data, you can use that. You try and cover that, but just that there is a relationship between the crustal anomalies that you can bring in lab, make some experiments, and reconstruct the core field. I'm the only one to do very scientific like this, but it is. So now let's go back to the crustal field. The general principle on this one, you have just here the flight, but it could be a boat, not here, but it could be a boat, it could be a UAV, vehicles. This is something that is commonly used nowadays. And a ship or satellite, the principles are the same. So you have a magnetic sensor, and in general, at very high altitude, the flight is just following a route that does not care much about the topography. It's very high. In some other places, it's following the topography. And so you have sediments here, and here you have layers that are geological layers. And the idea is that each time the magnetometer crosses an anomaly, well, a different magnetization, it captures the signal, and then you are making some grids, and then finally you are mapping the field. The thing is that by the time you end up the survey, the conditions have changed. Core field has slightly changed depending on the size of the survey. External field conditions have changed, and also the ionospheric conditions have greatly changed because ionospheric field is stronger during the day than during the night. So depending on the size of the region, if this is a full country, for instance, you do it over several months, then you have circulation, you have different ionospheric currents every day, you have the magnetospheric field varying according to the solar activity and a lot of other magnetic fields. So here, what I would like to show is that if you have a source here, this is the ambient field that is supposed to be constant over this small area, which is not true in general, but it will create a perturbation, a small perturbation of this field. So if the field is induced, this perturbation will be following the direction of the ambient field. If this is remnant magnetization, it could be in any direction. So the thing is that it will depend on the so obviously it depends on the composition of the crust, but also on its history. If you have tectonics, then you will have fluctuations, so it will give you a new contrast. And the thickness also, because what you see is kind of bulk magnetization signal, magnetic signal. So you don't really know exactly the volume, so you don't know exactly the composition, but at least you have the signal. So the game after that is just to do an inverse problem to try to separate between these primary parameters. So let's try with a very simple example. You have here, this is the direction of magnetization. The flight line is this, so it's going from here to here. And when it goes above this one, it will start recording a field starting from here. The field is increasing on top of the magnetic anomaly. And then it's decreasing. Very simple. If you now add this one is not magnetized, this one is not magnetized, this one is not magnetized, but they are all the same magnetic moment. If you just combine the three magnetization moment to produce the magnetic field, then the flight is following the same path, and it records the red one. So this is a signal of each. But actually, the flight records this kind of oscillations because the magnetic field is acting over long distances, and that makes things a bit complicated because it's not because you measure magnetic field somewhere that it is actually lying in the vertical. It can be somewhere else. Okay. Easy. It's very easy. Now you have two other magnetization, smaller, larger, and you see that things are getting a bit more complicated because signal is still the red one, but this is a superimposition of the three first one, plus there is one missing somewhere there, plus one green one plus this one, and it gives you the signal. It's there, but it's blue. Yes, it's actually there. But even. Thank you. Maybe I'm bad. So the thing is that you can imagine that measuring this and trying to go back to this is not easy. Especially because now this one and this one could be actually one single element instead of two. They could look like a single one center on this one, but maybe smaller. See how things are becoming tricky now. So the crustal field measured on Earth depends on the magnitude of the magnetization of rocks and their geographic distribution. And in general, why you perform geomagnetic surveys is because you know absolutely none of both. You don't know the magnetization, and you don't know the geographic distribution at depth. Of course, you have the geology, but underneath you don't know exactly what's going on. Okay, let's add something else. Now just change the directions of the magnetization. You imagine that there is some layer of magnetic that is mostly remnant, and it was completely flipped, which is not happening very often, but that's, yes, you do that depending on this case. But this one has flipped. So now the magnetization is locked in that direction. Those are freely induced. This one is kind of mixture of induced and free magnetization. And now the signal is completely different. This is the two green, because this one is in that direction, it's creating a small bump, then minus, going up. And this one is still almost directly in the same direction. And so you are measuring this one. So the thing is that now you have a signal that is varying with composition, tectonics, history, induced, remnant. I forgot something, but there are plenty of parameters. And the last one is that now you are introducing the topography. Sorry. Oh, sorry. So now you are introducing the topography. Topography of the magnetized rocks, because there is a sediment cover that is supposed to be non-magnetic. So the distance between this one and the ground is the same, but the actual distance between the ground, the plane, and the surface is no longer. But you don't know the thickness of the sediment layer. Not anymore. So now you will get this signal, which is basically the same one, but it's skewed. And so you can just add a lot of ambiguities like that. And one of them is very interesting, is that now you add thermal anomaly. So you have a small hotspot. Or you have a volcanic epicenter or something that is hotter than somewhere else. And above certain temperature, you lose some of the magnetization. So actually what you see is that it's reducing the signal you get. But I tell you that you get this. This is the only thing you get. And then you try to understand what's going on. You can have also geothermal anomalies, fluids, chemical alteration. I told you that you have plenty of parameters. And what you are measuring the magnetic field outside the sources. But you want the parameters inside the source. It's not complex, no? It's just something now, another one, is that everything I was talking about was here. So at one specific location. So the same crystal structures placed somewhere else on Earth will not give you the same signal. You know why? Yeah, because of the direction of the core field. When you have this three alignment, magnetization, and one was this, and one was this. Of course, this one were reduced, so aligning on the field, so I assume that the field was in that direction. But if you move because of the Earth, vertical direction is either here or either here. The sun is here. But now if you are here, direction is this is called the inclination of the field. The thing I was showing you earlier. So you have the inclination of the field and the declination of the field. If you assume a pure dipolar field, you're concerned about the inclination of it. So here, if you play around with the inclination, so now we are here, and we will slightly go to the southern hemisphere. This is how your magnetic anomaly evolves. So, same crystal structures, completely different magnetic anomalies. So the thing you do to everywhere you go, consider the shape of the core field. If you assume that it is a core field and correct for this effect, to end up with a map that actually is not changing anymore. You look desperate. Yes?
So when you do these kind of studies flying over a large magnetic body, do you reduce it to the dipole easier? If say I'm in Africa and I'm flying over a big rock, what magnetic field would be best for me? What magnetic core field would be best for me to subtract in order to get the ideal perspective? What's the ideal method for you to combat the effect?
So this is the idea. But the thing is that here we are talking about the flight line at a common altitude. It's very convenient. It's almost never happens. So, and if you want to take care about the inclination, you have if you use a black box like Geosciences or I don't know if you heard of these softwares, but they are using Fourier transform to map the field over a small area, consider the inclination, correct for this, and then correct for the angle. Correct and correct because the inclination is changing. Okay, so, and the software does not deal with varying inclination because it's designed for small areas. So over very large areas, there is no, I would say, there are recipes, but it's like experimental cooking. So it's not recipe, it's just guidelines. So the thing is that if you really want to map, you just want to map, you don't really care about what kind of coffee you want, because you don't want to try, you don't want to recover the properties of the first, you just want to map. But if you want to make some geophysics out of them, it's very important to correct the measurements with a very consistent core field, and that is consistent with time. So we don't have that for all time periods. We have that for the satellite based application. And then you have to correct for the external field, and then you can eventually get the actual signal, the true values. And then when you correct these true values for the information, you will get information about the bulk magnetization. Once you have the bulk magnetization, you don't know if this is the depth that is varying or the strength of the magnetization. That's even not ambiguity.
If I want to do anything like pseudo gravity or
Yeah.
up and down, no, I guess up and down information is fine. Then I have to make strip off chaos and
Okay, but I know what you mean. The thing is that if you want to do it with Geosciences or your own software,
my own software. No, some underground supervising. So preferably easy.
okay. So those have a problem because if you remove only the core field of chaos, depending on the size of the region, you will be left with large wavelengths. Okay? Whatever they are. And the thing is that this Fourier transform requires that you remove the constant. Otherwise, the Fourier transform is full of Gibbs effects. It's not the point here, but they don't satisfy Laplace equation if you have flux crossing boundary. So actually, if you have a very small size region, you have to remove the constant. If you remove the constant, you remove the large wavelength. If you remove the large wavelength, you are removing the information about the first. You are it's like a high pass filter. So I will show you an example of that because when we were trying to build the world magnetic anomaly map, we actually faced this situation. Okay. Okay, this is another example. This is a benchmark model created by the Society of Exploration Geophysics because they are very interested in this kind of problems. How to map properly the magnetic field, crystal field, and how to recover the sources. So what you can see here are the basements, which are the maximum depth of the magnetized rocks. So here this is deep, here this is shallow, and you have a fold here, and a second one here. And they placed bodies, very simple bodies, with different susceptibility values. So values that will create a different magnetic field in the same amplitude. So those are strong susceptibility values, medium susceptibility values, 0 here, and those are just smaller values. So you multiply both, and something I will discuss afterwards, that in each region you can consider that this one times this one represent a series of dipoles aligned almost continuously. And these dipoles aligned continuously will create a magnetic field here times the bulk magnetization, and you can represent the magnetic field, the synthetic magnetic field generated by these layers at any altitude. So it's kind of also upward continuation. And what you get is a vertical direction field. Inclination 0. Top is the basement, so it will be equivalent to, so you have this And then you just draw topography at the bottom where you have magnetization here and zero here. Okay. And within this, you say that this one that would be this one. This one is the susceptibility one, and you just play around with the rest. Okay. So you have a map of susceptibility, and you multiply by the depth for each one, and the depth is changing with the location.
So this model is in which plane is what?
Yes, sorry. This is yes. This is X, Y, and from here you will just place susceptibility values. Okay. And here this is the same map where this is still X, Y, but the color scale indicates the depth. And then you multiply. So here this will be shallow, so this will be blue. And red will be the largest depth. And you multiply both, so the 2D susceptibility map will just pile up to the bottom, from the surface to the bottom of the layer. And so it will create a magnetic field.
So this is just like a single, almost like one column.
Yeah.
But what about like 2 columns, maybe? Or not 2 columns, but like 2 different layers.
Yeah, or 3 or 10.
Yeah, it's just like this is assuming it's just one.
Yes, so it will be wrong. It's just not it's just a hypothetical model, and I will discuss with you afterwards why having a vertical distribution of layers doesn't help. You cannot.
Yeah, you wouldn't be able to.
You cannot have vertical information from
It's just in terms of. Could that be like a dipole? Like I feel like that's the only thing that you could really find is something that's like optically vertical that might be like a dipole,
Okay.
but not like a steel, right?
Okay, but you know what? I could actually do something like this. This could be 0, 0, but 3 different susceptibility values. They will just provide the same. To illustrate that with this a bit more complex distribution of sources, more complex than the simple dipole I showed you earlier, you have this kind of maps where for the inclination of the core field, where you recognize susceptibility contrast here, but they are modulated by the depth of the bottom of the sources. You see this one here? But it's not a single anomaly actually, it's creating also a small log. This is the vertical component. This one also is creating a kind of dipole and so on. If you change, if you are at some other place on Earth, you have a different signal. Go 60 degrees, another signal, and 90 degrees, almost the opposite signal as this one.
Ideally zero.
Yeah, so the thing is that from all these pictures, how to get only one single consistent picture. So that would be the interest of reducing everything to zero inclination to the pole. Zero inclination is equal.
So that's just induced magnetization.
Yes.
So you don't come for that magnetization.
Yes. Actually, we never talk about human magnetization except in the oceans because it's too complicated for us. And we also assume that lunar magnetization is small scale. Oh, I don't know. The contract, for instance, or the yeah.
Just a PhD project for you, don't have to worry.
Not sure.
So,
So,
you carry on.
no, but actually, these maps, I don't believe in these maps because they are all making the same assumptions. So the thing is that we are talking about geosoft softwares or black box softwares. They are all relying on the same assumptions, which are not true, and they are not very helpful for us to recover the properties of the rocks, whatever they are. So we need to do some physics. We need to take care of the specific area. We need kind of samples from in the laboratory. We need a lot of things. So just showing the usual techniques and how the shape of the map changes under the set approximations. Okay. So now, how do we get all this data? First of all, very nice place to monitor the field in real time, but very poor in space, magnetic observatories. And they are very important because when you carry a survey, when you want to make a survey, it's very nice to have a nearby magnetic observatory, so that you don't have to care about the effect of the external field changing during the survey. But it has to be very close also. The reason for that is that it's very difficult to make a difference from data sampling, the difference between a moving platform that will record space changes of the magnetic field and the time variation of the magnetic field that is not changing in space. You move. So we have planes, but of course they are covering small areas, sometimes very small areas. For very specific campaigns, like over Australia, for instance, they are covering huge areas, and they have deployed biometer stations, especially for correcting for the external fields, but most of the countries didn't do the same. We have marine data. Marine data, when most of the time the campaign is not designed for marine, for magnetometry exploration. It's kind of, you are just choosing a lot of different targets, and so you are following a route, and so you have track lines or a couple of track lines, and then you have to do something else with this data. And you have the satellite data. So before Swarm, that was launched in November 2013, we had the CHAMP. Ørsted also, but Ørsted was flying at very high altitude. It was launched in 1999. It's a Danish mission. It was at 900 kilometers altitude. Swarm is currently at 500 kilometers altitude. There are 3 satellites. 2 are flying side by side. So the idea is that thanks to this configuration, you can configure gradients, so that rather than using this ground-based station, you make a difference between both satellites. And so you see the very small scales. So they are supposed to record the same ambient field, but not the same cluster field. Okay? And we had the CHAMP, that was a German mission launch, and the DFZ participated a lot to this mission. There were actually filming many different things we are talking about today from satellite measurements. And CHAMP lasted for 10 years. And what is very interesting with CHAMP is that at the end of the mission, for the last year and a half, it reached very low altitude. So low altitude means closer to the sources, so data signal to moderation. Swarm was supposed to launch to last for 4 years. And since it's very successful, it's still very high. So for me, it's not very successful. So it's still very high, and they will just let the configuration like this till there is no battery anymore.
Can you not use the gradients even though you're quite high?
But the thing is that if you, for instance, you have these magnetic sources here from the crust, if you go at higher altitude, it will look like this. If you go at higher altitude, it will look like this. If you go at higher altitude, it will look like this. So if you take the gradients between these two paths, you don't see anything.
Yeah, fair enough.
Okay. So there is always a compromise between the gain of making the gradients and actually gradients are tricky because it means that the noise on each magnetometer add. So it's a square root of 2. So signal is small, but you're actually adding the noise by taking gradients. So it's not so easy. And if you can take the across gradients, the along track gradients. Some people are trying to make the vertical gradients, but it's not working at all because things are happening at 2 altitudes. Sometimes you have currents. So those are actually the 4 ways of measuring the magnetic field, and you see that at intermediate altitude you have nothing. The reason why you have nothing is because it's very difficult to make a satellite last for sufficient time to probe the entire Earth and to maintain at a low altitude because of gravity. So it would be impossible to do that. So now, I'm talking about this project because this is made under the umbrella of the International Association of Geomagnetism and Aeronautics. And this is a long-term project that was initiated in the early 1980s. But the thing is that there was the Cold War, so everybody, even if they don't know exactly what to do with the personal map, they didn't want to deliver the personal map. So we had to wait till 2003, 2004 to deal with the agency, to deal with the countries so that they can release one time after the other different maps. And the thing is that you have countries who have national maps, so they are in the public domain, and you have many regions in the world where it's just maybe the property of companies. So we don't have access to this data. The thing is that this is a small picture showing a big patchwork. So each survey was done at a different time. Each survey is itself a patchwork of different surveys acquired at different times. And sometimes we lost track completely on the history of the survey. Just stitched together and we don't know exactly how it was done. So of course, what kind of problem do you see with this? It's, sorry? Yes, there are plenty of gas. Antarctica is particularly difficult because actually you could fly there, but the conditions are too extreme, so that it's, an helicopter cannot fly more than half an hour, 45 minutes because the wind is too strong. So apart from the gaps, if you look at this patchwork, imagine the first survey was done in the 1960s and the last one today. What happened in between? What?
It's more precise now.
Yeah. Yeah, but the thing is that precision of magnetometers compared to the primary source of error is okay. Even in the 60s, magnetometer precision was largely sufficient. So here you have, I don't know, I just took one, 2004, 69, 80s, I don't know, compilation of many different surveys. What's wrong with this survey? You have to correct for the core field. do you know actually the coal field starting back in 1950s, 60s, up to now in a consistent way? We are not sure about that. Especially because I think we made an experiment with magnetic field model with Observatory and satellite data, right?
Yeah.
Okay. And did you see this all together? You are planning this all together?
Yes, that's right.
So with Observatory data, you reach what is spatial resolution you reach?
We did it just after degree 6, just using one.
Okay.
One
So degree 6, you could, with the actual distribution of Observatory, maybe it's robust to circle 8. So the core field is strong from 8 to at least 16. Sometimes people say 18, sometimes people say 13. So you are actually, if you correct the whole data with this model, you are still left, you still have a lot of large values from the core field. So if you want to correct for this core field, you have no possibility but to make a regional model. And this regional model will correct each panel differently. So when you stitch together everything, you have what? Lots of difference. Okay. And sometimes they were not quite the same altitude either. Because some surveys were done at 1 kilometer altitude in very flat areas. Over mountains, they just suddenly have 5 kilometer altitude. Over oceans, of course, by nature, it's about 4 kilometers above the surface. And so, anyway, so this one digital magnetic anomaly is a map. It's the best we can do at the moment. We are trying to reprocess everything to make this map useful for quantitative analysis, but at the moment it's more qualitative analysis. Another thing is that I don't know why, but everyone has his own coordinate system. You have number 1, 2, 3, 4, étendu from Zutton. You have the geodetic reference frame has changed over time, so some people use the WGS now, but in the previous time you don't know. Sometimes people use their own point of reference, and this point of reference is lost. So you have to adjust by hand. So you see different altitudes, 1 kilometer, 3, 3, 1, 500, varying, not together. So anyway, so you can still play around with this, and actually you end up with a Here is an example. This is the compilation for Europe for the large scale. So every small scale has been filtered out. This is from Russia. If you just put them on top of each other, reduce them at the same altitude, merge them with the map of Tokyo, everywhere you have edge effects, almost everywhere. Edge effects, because of this Fourier analysis. So I would say all the large wavelengths are wrong. So I think that you just filter it. And you replace everything with satellite data. Because satellite data are homogeneous, large scale. You have kind of noise that is varying with time, but at least the specification of the instruments remain the same. There is no problem about orientation. Well, there is problem of orientation because sometimes satellite is slightly moving, but at least this is the Geosciences reference frame. Everything is much easier. So the thing is that you filter out the large wavelength from all the compilations and you replace this large wavelength by satellite data. So satellite data and aeromagnetic data are fully complementary. Satellite data cannot see the small scales because they are too high. Aeromagnetic data are very weak in monitoring the scales larger than the size of the server. which makes sense actually because you're just making a survey here, you have no idea about the surrounding environment. And also because sources outside may contaminate, as I showed you earlier, they may also contribute to the measurements you are making here. So you filter out. And in the end, you have this first version of the map that looks very nice compared to the gaps you saw earlier. Is there the trick? The trick is particularly clear in those regions where actually you only have the satellite information. So those changes, those contrasts are not clear, just that the spatial resolution is not the same with the satellite and the satellite. And also you see a lot of very nice alignments, sometimes very geometric lines. And then this map was also using all these orange, right color, right? So, they are using a map for the magnetization of the ocean floors. They are using the chromes, 9.5 chromes. They are just putting magnetization values, calibrate. Just is not just, huh? But calibrating these values using few mining data, assuming that the chromes is not only below the ship, but following thousands of kilometers distances. And so you can create this map. But still, there are plenty of very nice information here. First of all, those are real data. So you see the inversions, so the magnetization, polarity inversions of the Earth's magnetic field over time, over the last 220 millions of years. Here, you have these quiet Cretaceous zones, which are times where the magnetic field stayed in the same direction. Here you have triple junctions, giving you a flavor of what happened about tectonics. You have also movements here, footprints. Here also, footprints of the opening of the Atlantic. Here it's not clear, but you have also correlation with heat flux in Tibet, because this is the highest places in the world, but because of there is a collision, the temperature is also high. You have this Sumatra here, very clear. And now the projection is not very nice to discuss seeing in the polar areas. But, what you see also is that you have places where magnetic field is more complex and stronger than in some other places. South America, Siberia, South Africa, Australia, and those are the craters, geological craters. Because
So there are many marine magnetic anomaly data sets that have been collected over the years and by both sides in the Cold War and by modern marine scientific surveys. So how are these data sets combined for the ocean basin? Are they like stacked or?
No, they are not stacked because they are not exactly the same place. So they are stacked really. The data we see for the ocean internet is rather complex because it's mostly done, it's not done in 2D, so it's done on track. And so there are a lot of people looking at data, removing outliers, filtering out, correcting for the core field. Since you are very far away from any observatory data, then you have information from the daily variations also. And then when they go back to the lab, they see if some magnetic storm occurred. And so if the data works, they can or not. Yeah, it's very complicated, and also sometimes you have a large density of measurements. I couldn't show it here, but because the routes are following the same route most of the time, and only scientific expeditions can go in some very specific places, but they don't cover very large areas. So sometimes you have a track starting from here, going here, and then you have a very small scale.
So the data is kind of processed in a way that is like consistent, at least on this map.
There is no standard way. Also because the magnetometer depends also on the ship compensation, depends on the distance from because the ship is a huge source of noise. So if the magnetometer is very far away, they assume that the ship has some kind of contamination. If it's too close, then you have more noise. Yes, marine areas are tricky. What else? So yeah, this map was published for the first time in 2007. That's not so long. And since then, a lot of efforts have been done to improve this map from the satellite data, reprocessing data also, better understanding about these locations, reference systems. And so for each region, sometimes you have a new version coming up every 4 or 5 years. So this is the version 2 of WDMAP, and we decided to get rid of this marine model, the normal model, Int'l model. So actually, you still see some strange things there and there, but it's not as strong as before. Yes. So next week, yes, very important information. Next week, the Geomagnetic workers will present the latest version. It's not WDMAP 3, it's 2.5. Just to show you the improvement, the rate of improvement. So this is the 18th of July. I think this is important because this can then be used to compare with satellite data and produce very high resolution model in terms of spectrum. And I will show you afterwards how this can be useful because this is not our map, but this is quantitative analysis that allows you to make some statistical studies to infer information in the course.
Are the big cities affecting the newsrooms because they are big buildings with a lot of iron or that kind of things?
Yeah, but it's supposed to be 5 kilometers per second resolution. The survey of France was 30 kilometers per second resolution. So if you don't believe the spatial resolution, the spatial resolution is in fact confusion between information content of the data and reading data reading. Here, for instance, and here, satellite data, this is 300 kilometers with a true resolution. So buildings have no impact. One of my favorite are Australian maps and South African maps. Very good. They are beautiful. Okay, now that was for the near surface data and how we can make calculations from historical data. Yes, I should stress that it's very difficult nowadays to get funding to perform a survey as we did before with airplanes over full time. Nobody wants to pay for it. Unless you do it with private companies. So let's start again with this schematic of the different contribution of the fields. So we are trying to have to end up with a robust cluster field model from space. First step, I wanted to detail this because usually this is the absolutely all topics of IAGA. There is nothing left. So you have instrumentation, satellites, and so you get the data. This is from Swan, for instance. You get the three data sets. You put them here in the database. Then you use observatory products like KP, GST. Have you heard of this indices?
Yes.
So KP is a famous outburst because of hence here.
It's not emit index.
So it's monitoring the state of the geomagnetic activity. GST is disturb storm
Right.
index. In case you have a substorm or magnetic storm or shooting storm commencement, then you use these indices that are derived very carefully at magnetic observatories to select the data. There is no point to use data that are spoiled with external too many external signals. Another measure is the S10.7, which is the flux of the continuous solar wind. And the interplanetary magnetic field you heard a little bit about this morning. Direction of the interplanetary magnetic field, even if the interplanetary magnetic field is weak, depending on this direction, it will enhance or deflect the noise. Okay, then you select by local time. Do you know why? You select only nighttime. Which one? Yeah. Which one? Are you talking about? Which external? Which external? Which external? Yes, the ionospheric field. And also we have the SQ is those are the two lobes following the sun. I showed you the movie. So there is also a balance between selecting data and having not enough data to go to very high resolution with respect to the spec field and contamination of the external field. So the balance is very tricky. So you have IMF, DST, KP will help you to select quiet, magnetically quiet days. And those are very useful to try to minimize the level of noise in the polar areas. Local time by selecting only nighttime data, but nighttime sometimes midnight from midnight to 5 o'clock in the morning. So it's a very short night. I sleep more. Because the ionospheric starts earlier and sometimes it's a little bit later. Magnetic lens is also. We split between mid-latitudes and polar latitudes. Do you have any idea? We never go to that. It's because when you do the inverse problem, you try to get the parameters. There is implicit assumptions about noise. Noise is Gaussian. The standard deviation everything is wrong. But at least you are more careful when you select measurements in regions where they have more or less the same statistics. If you try to make the inverse problem using polar areas and mid-latitude areas all at the same time, you also have another problem is that if you project the satellites which are near-polar, they provide you denser data set in the polar areas than in the polar region. So the thing is that if you make an inverse problem out of that, more noise in polar regions with more data, then you have more or less bias towards the polar regions. And also, it's because after all this, you still have to make dedicated corrections. So first thing is data selection is already a long process. past, everything was here. If you select this, you get rid. Okay, on my map, you get rid of everything. No, you minimize. Then you make a mathematical correction. So you get rid of this one. The problem is that by getting rid of this one, you are actually getting rid of the lithospheric field also, for the large scale. So far, nobody knows exactly what is the signal of the very large scales of the lithospheric field. From the size of rivers down to 2,500 kilometers. This is typically the overlap with the core field. So we are trying to reconstruct this because these scales are very important. Because if you look at the continental scale, like for the United States, for instance, I think from the east to the west, it's 5,000 kilometers, more or less. Is it about 5,000 kilometers from the east to the west coast? 3,000 miles for 5,000 kilometers. So you see that it's larger than, actually there should be different signals here. So if you want to play with the continental reconstruction, you are missing a very important information. Okay? Now, next. Okay. Sorry, I'm just. Oh, yes, it's out of place. Okay, main correction, and then we have external correction with big corrections. I'll come back to this later because we have a small break because it's not in the right order. This is actually a slide I should have showed you much earlier. This is the power spectrum of the lithospheric field at the Earth's surface, as it is measured by the world, and it is depicted by the world phenomenon map. And this is the same polar spectrum at the altitude of the satellites. And here, this is more or less the sensitivity of the magnetometer. So, you see that at 400 kilometers altitude, you are within the limits of the magnetometers and all the problems of orientation from space. So, this is why satellites, at least at 400 kilometers altitude, won't be able to see the very small scales. And I told you that airplanes don't see the large scales. This is why you combine both, keeping in mind that we think that there is a spectral gap. Do you understand what the spectral gap would be? You have full gain, full information content from some spatial scales. Here, well, it's not too clear. It's working, it's not working. So the gain is probably not very, very good. And from airplanes, I told you that some of the computations were based on patchworks, but some of the computations were based on patchwork that was very carefully corrected for. And so, again, there are regions like works, some of the regions work very well, some of the regions were not. So, this would be the spectral gap. We are missing information in a spatial range from 100 to, let's say, 600, 300 kilometers. Yes, this is because I was talking about configuration. So I wanted to talk to you about IRF, the other international geomagnetic constellation. So this is again a working group from IAGA. Indices working group from IAGA. Observatory working group from IAGA. Modeling the geomagnetic frequency working group from IAGA. WG9 working group from IAGA. So you are at the right place. So it's meeting every 5 years. So you have a standard model for the main field and the prediction for the circular aberration, and it's providing a revision. So this one is a new international geomagnetic reference field that is kind of consensus. Consensus is real time. So this one is a consensus. But the counterpart is that it's released every 5 years. So this is why some other groups are building models with circular variation and temporal evolutions on a regular basis every 3 or 6 months for their own. These models are very good and can be used for data collection, but they cannot be considered as internationally accepted models. They are more like prototype models. So there is a working group, 6 p.m. I know when we discussed it it's your time. So, but everybody is welcome for that because the head of the group is changing every 5 years. It's a kind of service to the community. It's very interesting because it's gathering 15 teams from all over the world. There is an evaluation process. You understand how the model is done. And this time, I think we will be voting the specifications or start discussing who will be willing to be part of this group and come with the candidate models. So this is something that is quite interesting. So anyway, let's go back to the core field. This is the vertical component of the magnetic field at satellite altitude between 2006 and 2010. Just to show you that if you compare two maps, you don't see any circular change, but they are there. So it's very important to select the model. You know, it's typically 4 years, the core field has changed. But you don't see this on the map. So it's important to create the data for natural core field. Then, now, if you don't correct for the magnetic field, what happens? The crystal field is behind. It's just at the second altitude. Do you recognize some kind of features you were discussing this morning? It takes 90 minutes to make one orbit. 45 minutes from here to here, the magnetic conditions have changed. So you've got some signal on the track. Here, it's quiet. Surprisingly quiet here, because usually it's not quiet. And then if you go to the other orbit, you have an offset, kind of offset, but in the opposite side. So you end up with kind of oscillations like that. Some of them being on the side of the crystal field itself, because the magnetospheric is large scale, but the time variation translates in terms of small scale, because of dislocation and so on. So you have to do something. So the simple thing is to correct the data along the track with a kind of external magnetic dipole. And for each 45 minutes, you correct for this. Sometimes it's working, sometimes not, because as you see, simple dipole doesn't work for over the entire track. So even if you do that, you improve the situation, but then you end up with a model, and I remind you that the model is obtained at 400 kilometers altitude, but you want it at the Earth's surface. So you are actually doing a downward continuation. And this downward continuation, because of let's take the potential. This is the potential. This is the magnetic field. You got the data from here, and you want to plot the data at equal A. So actually, you see that it's like amplifying each scale, the smallest scale, so the larger wave number, by n plus 1, exponential n plus 1. So you're actually increasing a lot the noise. You see what I mean? So here you recognize things that you were mentioning in this model. we will not see exactly what you saw this morning because this is an accumulation of several years of data. So sometimes it's there, sometimes it's not there, but the increase of noise towards the pole, and also these signals here, which look like yes. And here we also have spatial trouble like this because of particles going down near the poles. And the thing is that, of course, because this signal is varying very quickly, sometimes it's creating discontinuities in the signal, some offsets. And these offsets, if you do spherical harmonics, they will create ringing, because you cannot model a discontinuity with a continuous function. So you really have to get rid of the signal before hoping to highlight the cluster. So that was for the external corrections. No, that was about the problem of external corrections. And now, this one is probably too complicated, I guess. So if you assume, I just wanted to illustrate the problem because you could assume that the magnetic field is dipole, external magnetic field is a dipole along the track. The thing is that you don't separate internal and external field from a single half track. It's not possible. You see what I mean? Spherical harmonics are orthogonal basis functions. Does it ring a bell? Trigonometric functions are orthogonal basis functions. Does it ring a bell? It means that if you're looking for coefficients in front of the cosine and coefficients in front of the sine, they are separated. If you integrate, it goes 0 to 2 pi for the trigonometric function. Anybody? Okay. If you do that, if you put cosine x and cosine and x dx. I'll just put that back here. If you integrate, what does it do?
Cos.
It's cosine n times x. And n can be 1, 2, 3, 4.
So what
Cosine
about now?
x. Sorry?
We're talking about like orthogonality?
Yes.
Just in, like are you talking about just like separating the terms, like the real and like imaginary, until you get that like orthogonal?
No, I'm just trying to. I will not talk about the strike harmony. So let's make this a Fourier series. Alpha n. Okay, this is the Fourier series. How do you estimate these coefficients?
Integrate.
You can
Sorry.
multiply each term by cosine and x, and so because of orthogonality,
Yeah.
you extract. There is no correlation between the coefficients. You extract A0, you extract A1, A2,
And the
and so
eight.
on. Okay? This is due to the orthogonality of the basis functions. Strike harmonic are orthogonal basis functions. But what it means is that it is orthogonal on the sphere. It's not orthogonal on a single track.
Oh, okay.
Okay?
Yeah.
So if if you make the assumption that the magnetospheric field is external dipolar, might be true, varying with time, might be true also, but trying to estimate the coefficient of this simple dipole from a single track is not possible because you cannot separate all the functions if you don't integrate over the full sphere. So actually, this is an illustration here. How this is called the spectral leakage constant. Here, this is the true value of the external coefficient in spherical harmony. W, let's say it's 1. So it's Q1. This is the estimate you have by the estimate by your inverse program. This is the change, this Q102. And actually, this you can show analytically that the estimate one is the true one, modulated by all internal coefficients and internal coefficients. So actually, what you do is that you estimate the coefficients, that is the true one, plus a function of the crystal. Because you cannot separate internal from external. You should get a full sphere. Just because this technique is used very, very often, if not all the time, in planetary science. Why? Because on planets, sometimes you have 1 or 2 flybys before having daytime orbits, and sometimes you never have daytime orbits, just 1 flyby. And so people are trying to infer the strength of the external field and the internal field by this simple analysis along the tracks. But they are intrinsically flowed by this spectral leakage because economics are of over a sphere. So even when you do that, this hypothesis, even if the magnetospheric was purely dipolar external and simply varying with time, you are making an error because you are inducing some spectral leakage. Anyway, it's still working, more or less. Okay, now it's clean, except here and here. But here this is just discontinuities, because during the data selection process, when you are solving an inverse problem with the Gaussian noise assumption, if you have 1 or 10 or 100 wrong data out of millions, sometimes they will just bias the solution towards the wrong values. So here this is a reading effect. Okay, you can go further with dedicated corrections. And now it's completely subjective. So it depends on the data, it depends on the group, it depends on the fight, the groups, competitions. And everybody arrives with his own idea and saying that what was done before is completely wrong. And yes, here and here. Is it true? If not, nobody knows, but it's consistent with what you expected. You expected, you did not expect that. Looks like it's acceptable. So these regions are the most problematic regions because the external field is varying too fast, even during quiet times. So varying too fast, we don't have enough data. Even the gradients sometimes, because the gradients are not real gradients, because this is finite differences between 2 satellite data. But one sometimes is arriving earlier than the other in the noisy in the polar areas. And this simple time difference is problematic because the field may have changed already. The noise may have changed. It's improving a lot, but it's not sufficient. Okay, that's a clean one. But still, you see that this small stuff here. This one are genes, because they are following the oceanic dynamics. But I can tell you that genes because I know that. Here, I don't know, but I suspect that this is again some noise that was not fully correct before, and when downward continues to the Earth's surface is amplified. Okay? Is that okay?
Yeah.
Now or?
Whenever it's on your convenience. Like now it would be ready. So we should put in for you.
Because those are the most difficult to explain. So this is the main equation that is that was the purpose of the work in 2009, and it's coming. So the idea was to estimate by a synthetic problem. It's maybe coming. Yes. By a synthetic problem, like given our knowledge of the crust and the composition of the crust, even if it's not the real one or the actual one, try to make the variation of the induced field. So we just generated a layer of susceptibility values according to continents, cratons, geological structures, and so on, and topography. And we started in 2000 with the core field and played with the core field time variations, and we subtracted the estimated crustal field in 2020 from the one 2000. That gives you the time variation of the crustal field. Is it clear? And so what we observed is that actually it was over 40 years, because we used the comprehensive model theory Sabaka. I don't know if you know this model. And what we realized is that it's not constant in time, but it's not varying that much, but it's still there. Over 40 years, this is at the Earth's surface, the magnetic field has varied from 16 to -16, which means probably 100 Tesla per year, or half a million Tesla per year. It's not so big, but we have to be careful about that. And what is interesting is that even in the oceans, it's changing. Even though in the oceans, we assume that this is a magnetic field. The thing is that oceans have a topography, and these large scales are creating inducing field. The oceanic dynamics are remaining, but these regions are creating contrasts that are induced in the magnetic field. And you see that those are particularly important with respect to the magnitude we had before, in particular regions. Here, here, maybe here. Well, actually, here. And, okay, here. Do you have any idea why it's changing? Yes. It's because South Atlantic, so it's again related to core field. South Atlantic anomaly is going westward, and has changed. The location has changed a lot. It's not. The thing is that it's not a strong anomaly, but the gradient, spatial gradient of this anomaly, is important. So this gradient will reshape the crustal features, and you can correlate directly with the major changes of the circular variation between 2000 and 1960. And you see that major differences for the crustal field are in these regions. So the message here is that the signal can be accumulated over centuries, but it really depends on the spatial scales you are looking for. So it's there, but we can still use data from the late 60s up to now to make the math. even though we know that we are making some assumptions. So this was a very important question to answer, because otherwise, if, for instance, the small scales had changed too much in 20 years, we would have accumulated a signal that could be positive today with negative 20 years back and end up with a zero signal, for instance. It's not the case. Okay, now what can we do out of this stuff after accumulating the signal? So I need to go back to very simple fundamentals. The thing is that, okay, you have divergence free magnetic field, meaning that the basic element is a dipole. There is no monopole, it's a dipole. Okay, so it's, you can just express the dipole or the magnetic field of the dipole with the dipole moment with respect to a kind of constant and the distance from the observation to the dipole. Okay, this is a very simple geometry. And the thing is that if you want to interpret the magnetic field in terms of dipole, you have to place dipoles all over the crust. And to answer a question that was asked before about the vertical layering, if you put dipoles, so it will be plus, minus. So you put dipoles and you are looking by an inverse problem, you are trying to find the magnetic moment of each dipole. And you see that plus, minus, if you pile up dipoles, in fact, it looks like a single dipole. Because this one placed here will cancel with this one, with this sign, and opposite sign, opposite sign, opposite sign. So you end up with a single dipole. This is no surprise because this is a Gauss theorem. Gauss theorem means that you can express, when you integrate over volume, you end up with the expression of surface. So this is exactly the same. Okay. Another problem is that if you express the magnetic potential in terms of the magnetization times the thickness of the crust, which is delta H, you end up with a constant, of course. But the magnetic field is a granular potential, so the magnetic field would be zero. So each time you have a constant magnetization all over the place, you have a zero magnetic field. So you cannot go back to the full total magnetization, but only to contrast of magnetization. You are always missing. If this is a plane, for instance, or rectangular prism, you are missing the constant. It's impossible to go back to the constant. On the total Earth, this would be a shell. But it's not only this one. The thing is that you can demonstrate that in many places around the equator, mostly around the equator, you can just put magnetic structures in the crust. Assume that they will produce induced field, and the field will be zero. This is called the magnetic annihilators. So there are distribution of sources inside the crust that do not produce magnetic field outside. So the information, even if you manage to go back to the structure of the crust, the information is only partial because of this magnetic annihilation. Does it make sense?
So anything that is thick, has points.
No. The illustration was for the constant because the constant is very easy to demonstrate with this formula.
So which is like in the null space.
Yeah, numerically this is a null space. Okay. So it means that but from the physical point of view, you can make a distribution of sources and try to make an inducing field, and this is zero. Because this specific distribution do not produce magnetic field outside the Earth. Actually, they produce magnetic field inside the Earth. So those are called magnetic annihilators, and they are mostly shaped like this. So there are this, for instance, is a distribution of susceptibilities that gives zero values outside of the field. It's an important thing here because, as you can see, this is a magnetic annihilator covering almost the entire South American continent. So there is no hope to, even if we do everything carefully, there is almost no hope to recover the absolute value of the magnetization over this continent, because if you had a constant magnetization over the continents plus small scales or whatever, this constant is a magnetic annihilator in this place because of the shape of the Earth. Same for part of the African continent and same for some regions.
So, like, if it's following, it is generally following the equatorial, equatorial line. So that's where there would be no declination into the, like, is that why it would be?
No, it's not related to that. It's just related that imagine you want to describe the susceptibility over a surface like this. And since the economics are basis functions, you can extend every kind of basis functions. But so you have L, M, and that will be C, L, M. Okay. And in the same vein, you can write the vertical component of the magnetic field. Okay, let's write at the Earth's surface. Okay. And you said that this field is induced. This field is induced by susceptibility times the core field. And core field, you just assume that this is G10, just the dipole field. And then you can show that the GLM, which are the economic growth coefficients, they are actually dependent on LM, C dependent on M. So the growth coefficients depend on two parameters, susceptibility parameters, described in plus coefficients. And in fact, there are infinite combinations of these that give rise to the GLM equals 0. You can find as many coefficients as a combination. Coefficients are fixed. Okay, this is the distribution of your susceptibility depending on the structure. But you can find as many parameters, just constant parameters in front of that. If this one is 1, this one is 0, but this one is 1 and this one is 0, this is 0. But this one is a susceptibility. It does exist. So if you want to go back from this value which is 0 to this one that is not 0, this is then annihilated because the combination of those just produce 0 value. So 0 value definitions means 0 value of the magnetic field. You just do it for all terms. Yeah, it's a very caricature here because this is a combination of all equations giving the field to 0. But so you also can find some balance between the terms. But in any case, you see from this very simple example, at least this one, that combinations of non-zero susceptibility coefficients can give 0 value for the field. So So this is actually a problem because you can have, even if you think very, very nicely, you can only have an information if you go back from the magnetic field to the structure of the crust. You only have an information where something is missing. So you probably think that why is you care about this? There are so many problems. Because on planets on a global scale, from remote, you have gravity field, magnetic field. This is everything you have. Otherwise, you need devices on ground, lab experiments. And so if you want to, and on other planets, for instance, this is the first thing we do in psychology because we have no other need but the magnetic field and the gravity field to show the interior of the planet. So if this is not a complete information, still provides a lot of information. I will try to convince you later. So if you do that, there are very simple relationships. I'm not going into the details, but it's just that a simple dipole is very nice because you have this bell shape that I showed you earlier, and this bell shape crosses you at some point, here and here, and there is a very simple relationship between the size of the zero and the depth to the source. But this is the bulk depth to the source. And so dipoles are very fundamental in this kind of analysis. Then afterwards, for very specific geophysical perspective, people are using pipes, squares, blocks, and so on. Yeah, so there are, if you use very simple geometry, you can always find a direct relationship between the signal you have, assuming the shape of the source and the depth of the source. Then you go back to the depth of the source. So this is the law that has been known for a very long time since the very similar works of Natacharya, starting in the 1960s. He wrote almost all equations for the prism, for the sphere, for the pipe, for the dipole. Of course, it's not sufficient, but I think the key is here because if you manage to locate the zeros on both sides, provided you have reduced things to the pole, of course, then you have direct relationship with the 2 square of times the depth. Okay, now another trick. Potential field is combination of many dipoles now, just an infinite number of dipoles. And here, just to show you some experiments and why sometimes it's difficult to have information from. In general, if you have a perfect measurement, perfect distribution of measurements, you are in an ideal case. From one single surface, you could access information at any surface. This is actually what we try to achieve because I told you that we are measuring the field almost never at the right place. Satellite altitude for first fields, and even just switch for processes happening in the crust. So if you put 4 dipoles spaced, let's say 100 kilometers apart or 200 kilometers apart here, at 20 kilometers altitude, there is one negative polarity, one in 2 of positive polarities. Same distribution of dipole will give you this signal at satellite altitude, the airborne altitude of 100 kilometers of altitude. Okay, because if you go further, then the signal appears to be larger. Now you can play around with the 3 components. X, Y. Here there is important because there is something important is that here, if you go here, because there is almost no effect from this dipole, if you measure the field, the maximum is locating at the vertical of the anomaly of the structure. Here it's no more true because this one is acting on this one, so it's pushing outside or inside. So the maximum is not necessarily located at over the place of the anomaly. You play with the 3 contributions of the field and see that there is a cross here, occurring to merge X and Y. And if you take the Z component, and if you play around with those two components, now you can delineate the right position of the anomalies. But in general, we measure the intensity, because vertical, the vector field is very difficult to measure, especially at airborne altitudes or on the ground, because you need to have a very fixed sequence for CO2. Even on satellites, the reference frame on satellite is defined according to very remote, it's quasar. There is a catalog of stars. You have star cameras, and there is an automatic recognition about the shape of the sky, and then they know exactly the rotation of the angles. Except when one of the cameras is facing the sun, because then it's blind, and so we also have altitude problems for the satellite altitude. Now we can play around with this stuff and see that any combination will provide you with a different shape at a different altitude. So they vary in function of the strength and shape of the Earth's main inducing field, but also direct map depend on the altitude. So the thing is that if you imagine you are doing one day a survey at 20 kilometer altitude for this between 500 and 0, for instance, and the next day from 0 to 500 at a different altitude, you need to find a way to merge the information correctly, because otherwise you have a mixture of different views that definitely are not from the same altitude. Okay, let's play around again. Now, element of interpretation. We put random dipoles, so I don't know, just put 4 dipoles, random dipoles. Same 100 kilometer altitude. Now the structure is more complex. And now the satellite altitude. What does it look like? Yeah. So the idea here is that if you don't have perfect data, at the satellite altitude, a distribution, a complex distribution of randomly aligned dipoles will provide you with a picture of the dipole. This is exactly the same on Earth. For instance, when you go to the core surface, in the core mental boundary, the Earth's core field is complex. If you go very far away in space, it's dipole. So the idea is how can you correctly picture the field from this system. And I would know this. This is very interesting, at least to me, because on planets, you can find quite a few papers discussing the shape of these dipoles, for instance on Mars. And they try to find the direction of these dipoles, and on Mars this is renal magnetization, because there is no more dynamics. And they infer the direction of the instinct dynamo according to this dipole. But the thing is that the dipole was created by the random distribution of dipoles. So if you were doing the same job at a different altitude, you would get another picture. So does it mean something? I still don't have the answer. And some of my colleagues were not happy when I asked them the question. Because, but on Mars, for instance, depending on the outdoor, if they are looking at some regions, some anomalies, the dipole is not in the same direction, so they are discussing some maybe statistical direction. But if you go down, you go down to actually everything can be explained by random dipole. So this would mean that sometimes the dynamo was in that direction, but sometimes it's completely other direction. So this is still something that is used in planetology, but not too clear to me, at least. So if you measure imperfectly the field at this altitude, you will never be able to recover the exact distribution. And of course, we are measuring the field imperfectly at satellite altitude and the ambient condition. Okay. Now the reduction to the pole that we were talking about earlier, it seems that you are just, this is the dipole induced in ambient field with an inclination of 45 degrees. You reduce this, and now you end up with the vertical dipole. This is something that is very easy. You can find a lot of codes and book, a very nice book. But the thing is that it requires data on the same altitude on a homogeneous grid. So you need interpolation, Fourier transform, and reduction to the same altitude, something that people are almost never discussing. This is why I insisted on data processing, because otherwise you can find almost everything in the detail. Okay, there is a new challenge now, because unmanned aerial vehicles are commonly used nowadays to make surveys over active volcanoes, for geothermal resources, for any kind of resources. And the thing is that they are particularly efficient, but you have regulations. And you have a limited autonomy. And depending on the wind conditions, maybe for safety reasons, it's maybe better to fly at a higher altitude and so on. Plenty of different things that make these UAV measurements very heterogeneous. For instance, here, it's just a combination of different UAV measurements, because the small one can make a survey in 20 minutes. After 25 minutes, you have to push the button and go back home before it crashes, so otherwise you're losing everything. So you're actually making very small surveys. And sometimes if you go to a volcano, for instance, the survey is smaller than the size of the volcano. So you have to patch together all the surveys to make sure that you recover the full picture of the volcano. And another thing is that in remote areas, you can have the effect of the external field. And here, this is a picture of the magnetic storm that happened 23rd and 24th of April, 2023. You heard about this? Very nice aurora, visible from. Yeah. So here, if you go to a magnetic observatory, you get this time variation over. So it's in minutes here. So it's almost 2 days. 2 days. And if you correct the data for this stuff, you're still left with some noise along the tracks. So normally you should not use this data. You should have spent your day for nothing, because you are in a remote area, you want to cover a volcano, and it happens that there is a magnetic storm, so you're not aware of it, you still measure the thing, and in the lab, either you decide that you throw it away, or you try to make the best out of it because you went there and you. Okay. So if you try to make the best out of it, you're still left with this noise, which is a correlated noise in time, and added to the fact that you have data of different altitudes and sometimes not taking the same data. Then you need to set up an inverse problem for modeling the data and producing a consistent map at a single altitude, trying to get rid of the noise. This is another story, and we are discussing this next week. But these UAV are very nice because they will help us to bridge the gap between ground surface and aerodynamic measurements. Okay, so just to show that with specific techniques also, using potential theory, we can start from intensity data and recover the total field. This is very valuable. You can recover the north component, east component, and west component. So for instance, for this data here, required in this context, this is the intensity data. You can correct it for the core field and so on. You can recover the north direction. The east direction, you see that there might be a structure here in the north direction, minus, plus, and the vertical component that is showing you the lot of structure. Okay, now let's start with geophysical examples. This is for archaeology. Let's start small. Very, very small, but a small area. It's not so small because when you have to carry the 90 meters over a few kilometers and make stuff like that for days, just heading, going back 50 centimeters further away from the last track. But at least in the end, you end up with this picture. And this is a very beautiful picture, especially because we are not close to go back to Mari in Syria again. This is something that this is a big city of Mari, so it's like 4,000 years before now, or even 5,000, 4,000 before now. And you see that there are a lot of signals here. And this is very helpful for archaeologists because on the ground, of course, it's covered by sand. You can distinguish some things, but you don't know exactly what is important from them, from what is not. And here, for instance, there are many things that are interesting. When I looked at the map, I said, oh, but it's nice, we have roads. Not at all. Actually, an archaeologist, he doesn't care about that. He cares about this place, he cares about this, and he cares about this. Okay, why? This for him, it's too noisy. So if it's noisy, it's just for population, not interest. Here, this is large-scale structures, so it could be, like for the kings, for the sacred area. Here, this is the limit of the city. And here, this is the rubbish. Because if there is almost no structural signal, it's because everybody has just put everything in order. And so it will begin just to collect information about the daily way of life. I wouldn't do that. It's an archaeologist. So this is an example. So it's sign these kind of that I don't know if this is how many meters or this is let's say this is 500 by 500 or 1 kilometer by 1 kilometer. Another thing here, this is something you don't see from outside, but you look at the ground and you make the magnetometer measurements, and you see this picture, and when you dig, you see nothing. But you see this picture. Looks like a neolithic fence, nothing visible. Maybe how this structure was created. It's not an organism. It's not a
Like,
no. It's written here. It was built with wood, and the wood has been built. But the changes in the ground by just digging and letting the wood work make a small contrast in the magnetization because you are on the ground and you have another kind of ground. So in the end, you end up with this kind of structures. This is what I was telling you about the magnetic contrast. If you had a constant stuff, you would see that something is nothing else. But even a small contrast in the composition, depending on how small it is, of course, it will produce a signal. And now, if you look at the size of this, it's 4 to 5 meters between this 0 and this 0, and if you just use a simple rule like 2 square of 2, you end up with 5 divided by 2 square of 2, or 4 divided by 2 divided by 1.4, shallow. stuff where you just try to find out the zeros and the relationship between the distance between the two zeros and the last part. Yeah, it's fine. It's very simple, but actually no one will argue with you because there is nothing found in the world. So it's just to give you an idea, very rough idea whether it is worth trying to do or just to wait for somebody else to help you. So 1 meter is fine. Okay, now let's go bigger. This is the 6th impact pattern that was I think was monitored from the DXZ team. So they made some colleagues, they made some surveys, and they found that the impact patterns had this shape, and it was between the sea and the land. And this is Niemegk. Very nice place. And here, this is interesting because I don't know what they did with this map. But if you look at other planets, for instance, these structures are very interesting because they are concentric structures, but not completely concentric structures, and the direction of the compression and the dilation and compression give you a kind of orientation of the impact. And also, there is a maximum that is positive here. So, if you again compare with some other planets, in general, this is the remaining of the impact, which has a composition close to iron. So it's producing a high magnetic field by induction. And around, this looks like a negative stuff because you have demagnetized the crust by the impact, by the heat. And you see that around doesn't look like there is a lot of structures. In fact, there are, but the thing is that the contrast between this region and this region make this impact pattern like very visible. So we can do a lot of things actually, not from magnetism, but from this kind of pattern, because then some people have made some laws relating the size of the impact pattern of the impact patterns and the impactor. The demagnetization process means that if you have almost no more magnetization, it means that it's going to demagnetize very, very deep in the crust. So it gives you information about velocity, the energy that was delivered in the back and so on. Okay, this one you know perfectly now. This is the actually this is the base of plate tectonics. Dean and Matthews, when they observed the opposite direction, the line in the oceans, they decided that okay, this is the opening of the ocean floor, recording the polarity inverse of the Lithospheric field. So here you have the ridge, and you can see that this is not symmetrical because sometimes you have some folds on the other part, but and you can relate this with the stratigraphic scale that is done on Earth. So you can make a vertical direction on Earth and compare with the oceans, and you find out that they are pretty similar. So the thing is that this process, you have the ridge opening, and when it cools down, it records the Earth's field. So it's the line field, and when it's the polarity is reversed, it records the reverses. Which means that you can close things also. Okay, then we can close things. Here, this is just France is called the layer of this case, Spain, Portugal, and here you have a triple function that is something like a ridge that was stopped, that could not go further. And if you look at the scale at this one, you find out that these anomalies here correspond to somewhere around 110 millions of years. So you have the dating. And then, if you close slowly, you see that Spain has been rotating from Britain on the start here down, and then the Caribbean chain was formed almost at the same time, so around 18 million years ago, and then the Africa went down. So you can play around with this crystal information. Okay, that was illustration of how to use these maps for reconstruction or perspective. Now we try to make some statistical quantitative interpretations, and you need to write some physics. After this data processing, you need to write some physics. And the physics is complex, so you have to define the primary parameters. Is this a susceptibility, the first parameter on the global scale? Is this the thickness of the crust? Is this plate thickness? We don't know. So now I'm going up again at satellite altitude. This is the magnetic field at satellite altitude. No high resolution at this point. Just at 400 kilometers. So at the Earth's surface, no way I will try to interpret this. This is super complex. So I prefer it. So first thing to do is to check whether from satellite altitude this is mostly induced or remnant. This is important because if you want to reduce everything to the pole, you make the assumption that this is induced. If it's not induced, you are actually shifting anomalies in places where they should not be. So, industry should be aligned, and Stefan Maus and Fokker from the did at the very beginning of CHAMP an analysis using 2D Fourier transform, and they played around with two domains, continental domains and oceanic domains, and they made some power spectrum in Fourier analysis. And for each region, they just stored the power spectrum. And in the meantime, they estimated the shape of the power spectrum that should be provided by industry or remnant. There are two different power spectra. And then they plotted the values of the shape of the inducing field according to latitudes. Because of course, the induced field is more sensitive to latitudes because it's induced, and the field is 3 times stronger near the pole than near the equator. And the remnant magnetic field could be a little bit mixed up with polarities. So they make statistics. And what they observe is that this is the, if you go to the deep latitude, between minus 90 degrees and plus minus 90 degrees, they derive this shape. This is the theoretical shape. And for the ocean, they derive this shape. And they used it from lithospheric field models at that time. It was the beginning of time, so the models were not very accurate. But they realized that according to their analysis, on continents, it was following the induced theory, and over oceans, it was following the remnant shape theory. We did the same for some other models, and it would be nice to do it again with the most recent models. But the thing is that in the first approximation, the field is mostly induced over continents at these large scales, and the field is mostly remnant over oceans at this large scale. And this is a very important piece of information because we can start working now, saying that over continents, okay, we neglect the remnant magnetization at this scale. So, if you do that, you can write the power spectrum that should be the power spectrum of an inducing field in the presence of susceptibility distribution that is related to tectonics and so on. And this power spectrum depends on magnetization, crystal thickness, and a kind of power law that is the structural index of the crust. Nobody knows exactly what this structural index means, maybe nothing, but if you take the full power spectrum of the crust and you split between continent and oceans, over oceans, structural index is very different from the continent. This might be a very useful information because the process of plate tectonics that act mostly on continents because of the recycling of the oceans means that this is the power law. So my idea is that after billions of years of mixing, this power law will tend to zero because we have a perfect mixing. And this one is steeper because oceans are, we have long lineaments, so there is correlation in space, so it's different dynamics. So maybe we cannot go very far with these numbers, but I think they indicate clearly different dynamics, which makes sense. If you estimate the theoretical power spectrum with the observed power spectrum, you end up with some values which give you the magnetic crystal thickness on average on Earth. It's 26 kilometers thick on average, 32 kilometers thick in continents, 10 kilometers thick in oceans. We are not very far, but these numbers are very comparable to the lower models obtained in seismology. And the thing is that this is why I didn't specify it, but this is why we are always careful with the lithosphere and crust, because crust is structural information given by seismology. And magnetization depends on composition and also temperature. So there is apparently no reason why it should always stop at this crustal discontinuity. But in this case, it seems that statistically, the overall discontinuity seems to be also a thermal boundary for the magnetic field. So this is another piece of information because we have inclusive of continents and the depth seems to be bounded by the CC limit. So we have constrained already some parameters. Second thing is that, so I put this one, but I will skip them because it was for our colleague. And the thing is that this is for the global spherical harmonic model, but you could apply the same kind of analysis of piecewise to see if the depth and magnetization and structural index change with regions. And then you can gradually to recover the magnetic thickness of the large scales from magnetics only, given the fact that I told you that we are missing the large wavelengths of the magnetic field because they are being absorbed by the core field. So in general, we don't have access to the large scale information. But with these statistical models, here we don't see it, but we are missing this information in the crustal field model, But this power spectrum depends on the full depth, which means that small scales actually constrain. You don't need this information. With the small scale, you can still be seen in the parameter. You tell me if I go into details. I'm not going to do this. Okay, I need it. Just this is the crustal lithospheric field model over South Africa. 50 kilometers, 100 kilometers, 300 kilometers. See how the shape varies. So the idea now is to try to estimate, to infer the sources of this crustal field. So I told you that over South Africa, you have this crustal field. You can plot the spectrum, and you find out that the base field is 1.3, which corresponds indeed with the power law for the entire Earth continents. you estimate that actually it's a bit shallower than anywhere else. Well, it was 23, well, it's a bit shallower than the average. And the magnetization is 0.5 on top of it. This is also an information, because it means that the bulk magnetization is 0.5 plus minus 0. So you can have an access to the global composition. And then you can actually you could do it everywhere on Earth, and for each center of the region, you could estimate these parameters and recover structural indices, magnetization, and depth. Okay, now this is the field, and we assume that the depth is constant. It's 20 meters. And we consider now that the field is created by constant thickness, but varying susceptibility. And we obtain this map. If you compare this map with geology, it's not clear at all. We don't recognize anything. So, since I'm a very poor geologist, I will not elaborate on this. So, I will just now try something else. I will say that susceptibility or magnetization is roughly 0.5, and I will convert everything in terms of thickness. Okay. And now I get this one. And this one is not, it's interesting because if you look at the surface geology is very nice, but it doesn't give you information at depth. And in fact, if you go to these remote areas, you realize that the contours of the geology is very poorly known. But here, it might be a source of information for what's happening at depth. Here you have the Congo cratons. See that you have here. It's deep because cratons are colder, so they are deeper. You have the Limpopo bed, which is an old bed that is squeezed between two cratons. This one and this one. So maybe there is some information at depth to find the surface geology. At least those are just illustrations. The purpose is to now go forward and try to find quantitative information. Okay, anyway. On the global scale, let's go back to the global scale. What is the quantitative information? Inverse problem is difficult because you can explain everything either by susceptibility with constant thickness, I think I showed on South Africa, or constant thickness and varying susceptibility space. So now the only thing you can do is try a forward problem to see how it matches your observation. Forget about the inverse problem. So this was done, it has been done, it started for a long time. And the thing here is just to put constant susceptible magnetization over continents and constant magnetization over oceans, but slightly different, to make sure that there is a contrast between oceans and continents. And then you observe that you are generating magnetic anomalies. It's not sufficient to explain the crystal field from space. Remember that it was more complex. But at least here, it's not to explain. Now, you use the same, but now you use the topography at depth. Okay? And now you are making magnetic anomalies, this one plus this one, closer to the observation, but a little bit far away from the observation still. Now you deal with the oceans and you say, okay, over magnetic fronts, there is a magnetization value that we are measuring in the lab. I put these values all along the lineations and I produce the field. And this is the field over oceans that is created by this prime formation. You recognize the quite Cretaceous zones I was referring to earlier. So this one, at least, is not far from the observation. Okay, just one question here. At 400 kilometers altitude, you see that we only see the large scales of the magnetic anomalies in the oceans. Why? Yes, that's it. This one. Near the surface, you would get this, but when you go up, all the and to merge to give a simple structure. But anyway, let's go further. And this was the PhD thesis of Kumar Hemanth with Stefan Maus. They decided to take a geological map of the world, table for susceptibilities, more seismic maps, and put everything together with the layering of the given by the seismic models. And they generated an integrated susceptibility map, and they put this map into the organ field to generate the cluster. And they compared, they obtained this one. Okay? And we measure this one. And we measure this one. This one, 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 this one. So it's very nice because in the first approximation, if you combine information from geology, from seismology, we think that we are close to the observations. If you go to the spectral domain and make the spectral harmonic correlation analysis unit by degree, this is completely wrong. The picture is nice, the coefficients are wrong. The amplitudes are wrong also. But at least it's working pretty well. Okay? So next step, and it's still ongoing, is to really find out how to reproduce from a forward and inverse problem these observations. Okay, other kind of statistical interpretations now. I leave it for now because this is an open question. It's taking a long time to just consolidate the databases of susceptibility of rocks, geology that is changing because information obtained surface information are not valid at best and so on. But at least you can circle the major patterns and transform these observations in terms of susceptibility map because it's a kind of reduction to the code. And once you've done that, since it's reduced to the code, it's not depending on geometry of the earth. And then, once you've done that, you can close containers and see how the structures are following how the structures appear across the continents. And this is very exciting because it gives you information about where and what kind of continents are consistent at the Pangea for this one. You know here, the one like here, this is the same continuity of the anomalies, Yilgarn and the other Nelson, which are two different patterns, but in fact this seems to be the same unit. And you can go a step further and play around with this over millions of years. Do you know how we move these continents like that?
From combined efforts of humanity, tape
With a few steps on mankind. So, paleomagnetism. So now, Costa is also using paleomagnetism to obtain these kind of pictures because paleomagnetism has estimated the location of the continents according to hypothesis of dipole field. So it's not perfect paleomagnetism, but at the first approximation, we can plug the susceptibility map that is reduced before, plug the oceans, and go back. I stopped at 400 million of years, but the model is valid for the last billion of years. And what is interesting is that maybe this map can help refining paleomagnetism again. Because if there is some discontinuity between anomalies, assuming that we have no change in between, because over 1 billion of years, I think maybe things are happening. But at least you can see that there are lots of continuities. I don't know if, and this, you will not realize this otherwise. There is no, maybe gravity can give you information, but see, Madagascar here, it's here, and here it's joining again. Okay. Sometimes I don't know why pieces of continents are disappearing, but and then I will also give you an hypothesis. I think it's recorded, but it's very confidential. This Bangui anomaly is the subject of lots of debate. So usually, if you, in the literature, they think that this is an impact pattern. Why not? The thing is that if you go back to history with this, I don't know the date. I don't know the date of the Bangui anomaly, but just follow the Bangui anomaly. It's going south. Okay, it's at mid-latitude. It's going south. Okay, it's going there. And at some point, it should be going down. And I think the dating of the Bangui anomaly is several hundreds of million years. But the thing is that from probability, it should not have happened easily, because if you look at the system solar model, you have impact patterns that are very big, and the size decreases with time. And if you look at the size of this impact pattern, you can find on this astronomical linear scale kind of dating for that. Dating for that should be around 300 to 400 million years. If you take the size of the impactor. And if you take the size of the impactor and you relate it to this scale, then the thing is that an impactor, to impact the Earth from the south, like that, in the solar system, has a very low probability. Usually they are just impacting with some different angles, but from below or from above, it's reducing even the probability. So this could also help deciding whether, from a probabilistic point of view, an impact pattern could have occurred at such a low latitude. Okay. Now, once you have this susceptibility map, you can also play around with the spectra, all of the mirrors, the dipole, and make kind of estimate of the crystal thickness. And this is the estimate of the magnetic crystal thickness, which means the maximum depth at which rocks can sustain magnetization. Below, no more magnetization. And you see that it's very close to the seismic model, at least in terms of the amplitude. There is no evidence that we have magnetization in the membrane. This is important for metal composition. For metal composition, water content, and a lot of information, heat flux also. And so this magnetic anomaly map can help also resolving quite major scientific issues about the thermal regime of the Earth. So we have prepared this map. We are very happy to present it next week. And with some and co-workers decided to publish a paper not exactly on that subject, but nearly 3 or 4 weeks ago in the field. You probably know this group, the group, in the universe, like people that are very active, very self-sufficient. So I need to discuss with them. Okay, and finally, another example, because I planned to discuss what I told you that there are not so many planets where you can find first eclipse. In fact, you have Mercury, you have the Moon, and Mars, and for the planets, either they are not close planets or they are not here. So, again with the impact craters. On Mars, what you observe is a crystal magnetic field. It cannot be induced. It's human because there is no more core field. So the thing is that if there is no more core field, there is a essential question about when did the dynamo die? What time? Why? Because we are discussing this morning that without the Earth's magnetic field, all the atmosphere would have been wiped out, and then all the water content is wiped out, there is nothing. So in a very short amount of time. So this is the magnetic field. So the problem is why you see then here on Mars it stops. So this question is not resolved, but the timing of the extension of the dynamo of Mars is not resolved either. But the thing is that it has been thought that the dynamo will stop around 4.1 billion years, which is not a long-lasting dynamo. And the thing is that thanks to magnetization, the mapping from space with the MAVEN mission and the Mars Global Surveyor mission, we were able to merge together all this information to have a very high resolution map. High resolution map in planetary. So, but it's still depicting anomalies as small as 150 kilometer resolution. So, it means that 150 kilometer resolution means that you can start making some statistics on the large impact craters. And there are plenty of large impact craters on Mars. And of course, the smallest impact craters you don't have access to them because the model is not accurate enough, is not resolved enough. So if you look at this, big impact craters should have demagnetized the crust. So if the dynamo was extinct, then this should be demagnetized. But if the dynamo was still active, then it should have been demagnetized and remagnetized in the ancient Mars dynamo field. So we should have a signal. So the idea was just to find out, to make some statistics about the craters that were fully demagnetized and the craters that were not fully demagnetized. And according to this, dynamo persisted to at least 3.80 years. So it doesn't look much, but in fact, this is interesting because many authors working with completely different disciplines observed some features on Mars surface that they related to the water system. And they had a very hard time to justify their findings because without a dynamo, there would be a Mars magnetosphere or Mars big field protecting Mars from the atmosphere of Mars. And now, if you justify the timing, then it complies with the target water erosion in Mars. So this also has potentially a lot of outcomes for the internal and external dynamics of Mars, and if you transport it to any planet of the system, the solar system having a crystal field, you can infer the same kind of analysis. So again, the conclusion here is that we are measuring quantity that is related to many physical parameters. We are measuring this quantity somewhere we are not very much interested in, except in external external field in the external field community, but for the internal field, it's never where it happens. But if you use the multidisciplinary science, you can reduce the ambiguities and get very primary information. How to do that? You can do it fast.
Oh, really?
Yeah, yes, we are really.
Okay, well, thank you, earlier today. And, okay. There, I bet there are several of questions that this can be discussed also later on, I guess. And we will be around also tomorrow, I guess.
Tomorrow we'll be attending the
Yeah. Yeah. And also series of questions.
Yeah, really? Okay. Can I just use 3 minutes? Yeah.
Okay.
Because this is something just to tell you that when you are investing in crystal field, you have to look at all sources. And so we discussed the core field, and you have to make yourself the core field correct your own data. We discussed the magnetospheric field. I told you about these very primary corrections. But the thing is that these primary corrections, if for the external field, remember this offset? You don't remember anymore? Okay, let's get this one first. This is the effect of the magnetospheric field. You know, the effect of the ring current. Assume ring current. If you assume that the ring current is a dipolar, it's not a dipolar in the geographic reference frame, it's in the inclined reference frame, then you can estimate the internal, the external field, but also its induced counterpart in the Earth. Because there is something I didn't tell, but that is very interesting. Any time variation of the external field induces a response from the Earth, a global response from the Earth. This response depends on the electrical conductivity of the Earth's mantle, down to the core, but mostly the Earth's mantle, because we don't truly access to the very. So if you manage to get a time series of this estimate of the magnetospheric field in terms of the dipole and its response, you get a time series over 20 years, okay, of the external field and its response, from which you can do kind of magnetospheroids inversion analysis. And you go back to a profile of the electrical conductivity of the Earth's mantle. And you will see the germs of the electrical conductivity occurring at 1,000 kilometers down to the core. So you can use a lot of information out of magnetics. I should stress that this algorithm was prepared also for the swarm mission. And we prepared one 1D algorithm. Some other people prepared some 3D algorithms also. And what is very interesting is that I am in a lab where people are doing high pressure. And so they are trying to simulate rocks at depth down to the core mantle boundary. And so they have tables depending on the electrical conductivity of the minerals. And so you look at temperature and pressure. And some many other parameters. And the thing is that you can use these tables to make a secondary inverse problem from your electrical conductivity profile in terms of temperature in the mantle. So we can actually access temperature in the mantle also for magnetics at 400 kilometers altitude if you use the correct information. We can go a bit further, is that if you have a temperature profile that is more or less robust, you can extract a diagram of composition of the mantle. So you can close the loop. You started with some temperature and electrical conductivity, And then you can solve this electrical conductivity and temperature is a kind of combination of different minerals. Fraction of minerals you don't know. And then you solve by inverse problem for the fraction of these minerals that you should expect in the method, and you end up with a map showing you the fractions of different minerals in the method.
Okay, so if there are no further questions at the moment, quite early, but it's a really long day all in all, then let's end here.